Question 11.4 was pretty challenging question. It's a couple different calculations involved to kind of see if we put 42 kilojoules of heat into a 32 gram sample of liquid methane at minus 170 degrees. Number one, what's the final state of the methane once it equilibrates? And then number two, what's the final temperature? And then they give us the specific heat of methane liquid and methane gas, as well as the heat of vaporization. So the first thing we want to look at is we're going to have to take this methane that's at a minus 170 degrees and warm it up to the boiling point minus 161.5. So what's the energy required? So the first thing I did was, because it gives us the specific heat in joules, I converted this energy into joules. So 42 kilojoules, and we know for every 1 kilojoule there are 1,000 joules. So we're working with 42,000 joules of energy. And so the first thing, as I said, we've got methane, and it's a liquid at minus 171, minus 170, and we're going to heat that up to methane, still a liquid, at minus 161.5. We're going to see, do we have enough energy to do that, to heat up this sample of liquid methane from minus 170 to minus 161. So what's that energy going to be? Well, we look at the specific heat, and the specific heat is 3.48 joules over grams Kelvin. So what's our temperature change that we need to do? So that's the next thing we have to calculate. So we have 170 minus 161.5. Our temperature change is 8.5 degrees. And we need to remember that, right, 1 degree Celsius is the same change as 1 Kelvin. So this changing the temperature 8.5 degrees Celsius is the same as changing the temperature 8.5 Kelvin. So we've got a 32 gram sample, and we're changing the temperature 8.5 Kelvin, and we know for every 1 gram and 1 degree, it's 3.48 joules per gram Kelvin. So multiply all those across, grams and Kelvin cancel out, and we're left with 946.6 joules of energy. So that's the energy required to take it from minus 170 to minus 161. As you can see, we started with 42,000 joules, so we still have a lot of energy left. So the next thing, now that we're liquid methane, the next thing we're going to do is convert that liquid methane now to methane gas at minus 161.5. So the energy required for that, we're going to need to use our heat of vaporization, and again, that's also in kilojoules, so let's just convert that real quick to joules. So we have 8.2 kilojoules per mole, and we still know 1 kilojoule still equals 1,000 joules. So we're looking at 8,200 joules per mole. And then the next thing we need to look at, we have 32 grams of methane. Methane is CH4, which is 16, there's a molecular weight of 16 grams per mole. So if we have 32 grams of it, we have 2 moles. So 2 moles of methane. The energy required to turn 2 moles of liquid methane into 2 moles of methane gas is approximately 16,400 joules. So here was step 1, here is step 2. So now we've used this energy to heat up our sample to minus 161, and we've used this energy to take our liquid sample and turn it into a sample of gas at minus 161. Now we need to look and see how much energy do we have left.
Sorry.
So we've used 946 joules for the first step and 16,000 joules for the second step. So we want to see what's the energy we have left. And that energy is going to go to the final temperature change. So we started with 42,000 joules. In the first step, we used 946.6 joules. and in the second step we used 16,400 joules. So at the end of the day, we still have left approximately 24,653.4 joules. So we have some energy left that we can do some work. And what's that work going to do? It's going to increase the temperature of our sample of methane gas. So we want to find out how much temperature change we're going to see. We need to look at what's the specific heat of methane gas, and that's 2.2 joules per gram Kelvin. And so the first thing I did was, well, we have a 32 gram sample, and let's say what's the energy required to change that 32 gram sample 1 Kelvin. And that energy is 2.2 joules per gram Kelvin. So we multiply across, grams and Kelvin cancel, and we're going to find that for 1 degree, it's going to be 71.4 joules. So we have 24,653.4 joules of energy left. So if we divide this energy required to heat the sample up 1 degree Kelvin into the total energy left, we should be able to find what's the total temperature change we can undergo using the energy remaining. So 24,000 divided by 71.04 gets us approximately 347. So that's how many Kelvin we can change this sample of methane gas at minus 161 at the end of the day. We can add 347 Kelvin to that. So what's our final temperature? Well, if we start at minus 161 and we add 347 to that, our final temperature is going to be approximately 185 degrees. And remember, even though this was Kelvin, because the change 1 degree Kelvin is equal to 1 degree Celsius, it would be the same as adding 347 Celsius. So our final temperature is 185 Kelvin. So number one, we convert the methane gas into liquid methane. We still have energy left, and then with the energy remaining, we heat that sample up from minus 161 degrees all the way up to 185 degrees with that remaining energy. But we had to do that in 3 different steps. The steps, number 1, to warm the methane up to its boiling point. Number 2, the energy required to boil that methane. And then number 3, the remaining energy that was used to increase the temperature of methane alone.